whole topic within itself. And it's important that you understand the different elements of what causes resolution to be either good or not so good. First, we need to consider what resolution means. Resolution is a term used to describe how well you can see structures on the ultrasound images, either in detail or maybe time-wise, in moving structures. Within ultrasound, diagnostic ultrasound, there are several different types of resolution, and they're all important. The really important ones are spatial resolution, there's contrast resolution, and there's temporal resolution. They're the ones I'm going to talk about now in this session, as I said. There are a couple of others. There's one called grayscale resolution, which is rarely used these days, and I'm not going to inflict that on you. And there's also color resolution, but that's more a Doppler thing, and that will come in Doppler discussions, not in here. I'm going to be talking about grayscale beam mode resolution. Okay, so first of all, I'm going to head off with spatial resolution. Now, spatial resolution is probably the one you come to think of. If someone says to you, oh, what sort of resolution are you getting out of your ultrasound image? Spatial resolution is the one that comes to mind. It's the one that will determine how small the structures you can see on your beam mode image, how fine the detail is there. So it's the ability to differentiate small structures on the image. There are two types or two aspects to spatial resolution. Axial, which is along the axis of the beam, which will be vertical on this image, and lateral resolution, that's side by side or across the field of view, horizontally on this image. And each one of them, axial and lateral resolution, needs to be looked at separately, because there are different aspects of the beam that cause the resolution to be different. Now, spatial resolution can be affected by a number of different things within your ultrasound. It will be affected by the beam itself, the characteristics of the beam, the width of the beam, the frequency of the beam, that type of thing. And in fact, that's the one that I will probably be talking about the most here. But lateral resolution also depends on line density, how close the beam parts are together, and we'll mention that. It can also be affected by the image memory in your machine. Maybe it's a less expensive machine and it doesn't have as good an image memory as another machine, and it could cause a degrading in the spatial resolution you're getting. And finally, the viewing monitor itself could affect it if you've got a low resolution type viewing monitor. So all those things are going to affect it. But first we're going to look at the beam characteristics. And the first aspect of resolution I'm going to describe is axial resolution. Now remember, axial resolution is up and down the screen. It's the closest distance two structures can be along the axis of the beam that you can still see as separate entities on your ultrasound image. So as you can see here, we've got a beam coming down through the patient from a transducer. We've got 2 point sources here within the patient. They are clearly separate from each other. On the monitor down here, you're getting 2 echoes. The echoes are clearly separate from each other, and therefore you would say that these structures are resolved. These are clearly resolved. Now, if those structures move closer together, the echoes, logically, will move closer together. And in this case, the echoes are very close to each other, but they're still separate. These structures are still resolved. Just resolved, but they are resolved. Now, if the point sources get closer together in the patient, in this particular case on the right, the echoes from those two have merged in with each other, and we cannot discern them as separate entities. So those two entities here within the patient are not resolved. You no longer have axial resolution at that sort of distance. So now we need to think of, well, what's restricting us? What's causing axial resolution to cease at some point? Well, it's all to do with the pulse of sound. The pulse of sound has a certain physical length. It's called the spatial pulse length. Now I'm showing a little packet of compression wave here, a pulse of sound with 1, 2, 3 cycles in it. And it has a certain distance, a certain length. It depends on, firstly, how many cycles there are and how far apart each cycle is. In other words, the wavelength. So it's got a certain depth, a certain distance. Now I'm going to show that pulse coming down and striking 2 interfaces within a patient. At the moment, I've put the interfaces the same distance apart, whatever that is. If it's a 2 millimeters spatial pulse length, at the moment I've set the interfaces at 2 millimeters apart. Let's see what happens when that pulse hits them and starts to return an echo. There's the pulse going down, strikes the first interface. The moment it does that, it will start to return an echo, and it will continue to return an echo as it passes through that interface. The echo will be a mirror image of the pulse itself. Do keep in mind one thing here of my graphics. I am showing the echoes coming back offset from the pulse. That is for clarity. In actual fact, the echo would be coming straight back up from where the pulse came down. All right, so just keep that in the back of your mind. But I think it's clearer if we can just push it to one side to see what's going on a little bit clearer. Okay, so the pulse has now gone through the first interface. The echo of that interface is now heading back up towards the transducer. At this point, the pulse is now touching the second interface, and it will start to return an echo from that interface and will continue to do so as it passes through it. And there we have the echoes from the 2 interfaces going back up the transducer. My question to you is, are those echoes clearly separated? Well, of course they are. Look at them. They're completely separated. They will strike the transducer at separate times and be registered as separate echoes. So they would be clearly seen as 2 dots of light on your screen. Clearly resolved. No problem at all. Okay, now let's move those interfaces closer together. I've now dropped the interfaces down to half of what was before. So if this was a 2 millimeter long pulse, I've dropped the interfaces down to 1 millimeter. Let's see what happens now. So here's our pulse coming down and striking the first interface. Oh, look, here's the little echo starting to poke its nose up and heading back up to the transducer and being generated by the pulse as it moves through. So as the pulse moves through that interface, here's the echo from that interface being generated, heading back up, everyone's happy. But the pulse has now started to hit the second interface. Okay, so it's still going through the first one and it's striking the second interface. It will start to return an echo from that interface. So as it moves through, here's the echo from the first interface, and now here's the generating echo from the second interface, and there the 2 echoes from the 2 interfaces moving back to the transducer. I ask you the same question. Are those echoes clearly separate? And the answer, no, they're not. Look, they're touching. They will strike the transducer and the machine will detect them as a single echo. Longer echo, perhaps, but a single echo. It will not be able to discern that there are 2 separate echoes within this. So that will be seen on your screen as a single bright dot on the screen. In other words, those 2 interfaces are no longer resolved. We've lost our axial resolution. It occurred as soon as those two interfaces got to the point of being 1/2 the spatial pulse length apart. So axial resolution of the beam is directly related to the spatial pulse length. You can imagine in this case, if we shortened the pulse, all would be well. Both of these would be shorter and they'd be separated. But because the pulse length is this long, that occurs. So it's directly related to the spatial pulse length here. In fact, it's equal or theoretically equal to 1/2 the spatial pulse length. So if you can work out the spatial pulse length divided by 2, you will have what the machine is theoretically capable of producing you axially on the screen. Now, the spatial pulse length can be calculated. All we have to do is know how many cycles there are in it and the frequency of the transducer, from which you can calculate the wavelength. So the spatial pulse length is simply the number of cycles multiplied by the wavelength. So the spatial pulse length is primarily affected by these two things. The frequency of the beam. Higher frequencies, you remember, will result in shorter wavelengths. Shorter wavelengths give shorter spatial pulse lengths and therefore better axial resolution, which is the reason why we try to use the highest frequency transducer that we can for our scanning. The trade-off is that higher frequencies get attenuated more in patients, and therefore they won't penetrate as much. So if you do want to penetrate deep into the patient, you have to use a lower frequency and you will sacrifice some axial resolution. But if you can, use higher frequencies and you'll get the best axial resolution. The other thing it's affected by is the number of cycles in the pulse, and that's decided by your transducer design. If you have better damping in the transducer that will stop that element vibrating faster, you will get fewer cycles and therefore a shorter spatial pulse length. So you can't change that. That will be in the design of the transducer itself. But nevertheless, those are the two things that will primarily affect axial resolution. However, there are other things that will affect it as well. Axial resolution will be affected by your output power and gain. Both output power and gain affect the echo amplitude. Increased power, increased echo amplitude. Increased gain simply means the amplitude of the echo is amplified more in the machine and it's made bigger. Now, when you make the signal that you get in the machine bigger, you expand it not only in this amplitude direction here, but can you see it also expand slightly in the time-based direction? In other words, it gets wider. If you amplify that echo more, you increase its length. So if you increase the output power and gain to increase the amplitude of the echo, you will make that echo longer and you will degrade your axial resolution. If you put it in terms of the brightness of the dot you get on the screen, I think it becomes probably a little bit more logical. Here's your little tiny dot of light caused from the echo in the patient. Here is the amplified one more, it's much stronger, and therefore the dot of light's going to be larger, it's going to be brighter. And you can see it's wider, and therefore it would merge in with the next one beside it faster, and therefore the resolution will be worse. So spatial pulse length is going to be affected by those two. Okay, now also your image memory in your scan conversion process can affect it. For example, a 5 megahertz transducer, 3 cycles in a pulse. Now, if you did the calculations on that, worked out what the spatial pulse length would be, you would find that the machine, with the spatial pulse length, if you worked it out, would work out to 0.92 of a millimetre. Therefore, the machine would be capable of 0.46 of a millimetre of axial resolution. Not bad, very good. If you have an older type image memory of, say, 256 pixels by 256 pixels, and some machines were made like this, the older machines, it was very common, and you set your field of view depth for 20 centimetres, if you did the mathematics on that, you can work out how much anatomy would be shown along the depth here in each one of these pixels. And in fact, if you divided that out, you'd find that each one of these pixels would represent 0.78 of a millimetre of anatomy within there. Now, 0.78 of a millimetre is worse than the theoretical possible resolution of that machine. Therefore, this image memory would restrict your axial resolution to 0.78 of a millimetre. You wouldn't be able to get any better than that, even with a higher transducer. Okay. However, if you used a much better, more modern image memory, if that was in your machine, and the more common memories now are 512 by 512 pixels. Therefore, instead of 0.46, instead of 0.78 of a millimetre of anatomy in each one of these, you can imagine now it would be 0.39 of a millimetre of anatomy in each one of these pixels in your better image memory. 0.39 of a millimetre is better than the possible resolution from your transducer, and therefore this will not be restricting it. So you would have improved your axial resolution by changing from this image memory to this image memory in the machine. They actually experimented using image memories of 1024 by 1024 pixels. Expensive. And they said, wow, we should get really nice tiny pixels here. That should improve our images. And in fact, it did. Because suddenly axial resolution was restricted by these pulse, the beam itself, the spatial pulse length restrictions in axial resolution. And yet, I'm going to sound a little bit like a broken record at times here, because I'll be saying quite often, you can do all these things to improve your resolution, but you can never get better than what the beam geometry itself can produce. That's the final restricting factor. So yes, you could use super good image memories, but you can't get better than your beam geometry. Okay. Now, another way you can improve axial resolution, use your right zoom feature, or pre-processing zoom feature, as some people call it. Now, when you do that, and you put your little box there to do your right zoom, and you hit the go button, it will expand that small area over your entire image memory matrix. So if this was 20 centimeters down here with your original field of view, and you only wanted 10 centimeters of field of view within here, suddenly that entire image memory matrix is 10 centimeters. So you can imagine the amount of anatomy shown in here is much smaller. So effectively, you've improved your pixel resolution by using your right zoom feature. Okay, so that's good. The same thing will occur if you reduce your depth of field of view to the minimum necessary. Now, you should be doing that for a variety of other reasons, but here we've got 10 centimeters on the left, certain amount of anatomy in each pixel. We've reduced it to 7 centimeters. I think it's logical for you to see that the amount of anatomy in each one of these pixels is now smaller, it's less. Therefore, you've improved the pixel resolution within there. Broken record again. It'll improve the potential resolution, but it can never go beyond what the beam can produce in the first place. do keep that in mind. But someone might ask you, what are all the different things you can do to improve your resolution or your spatial resolution? Well, reduce your field of view. Use your right zoom feature. Okay. And finally, of course, the television monitor might have the potential to degrade it. You might be using a fairly low-cost portable ultrasound machine, and some of the monitors on those might be somewhat less than your nice fancy digital, large display digital monitors on your bigger machines. So yes, if they've got a poor resolution, that's going to restrict you. Now, axial resolution is not affected by the distance from the transducer. Okay, it's the same all the way down. You optimize it by using, more or less refreshing what we just said, use the highest frequency transducer you can, drop your power and gain settings down to the minimum necessary to produce good quality images, utilize your right zoom feature if you want to make the image bigger, or drop your scanning depth down to the minimum necessary. But they will all help. Okay, now let's look at lateral resolution. Lateral resolution is the closest distance to structures at across the beam, 90 degrees across the beam at the same depth, which you can still see as separate entities. Here's 2 point sources in a patient. Here's the 2 echoes on the screen, and those 2 structures are clearly resolved. Here, the structures are closer together. These 2 structures, the echoes from them, have merged in with each other. They're not resolved. So that's what we're talking about with lateral resolution. So let's see how the image is built up in this particular fashion. Now here's our transducer with this beam coming down. Yes, please, I haven't focused the beam. Okay, it was a bit harder to draw. But at any one depth, it's going to have a certain distance, and that's all we're interested in at this point. So here's the beam coming along, and it's going to move across, building up the image. As soon as the edge of the beam starts to hit the first interface, it will start to return an echo. It will continue to return an echo as it moves across that interface. Here, the beam is in between the 2 and nothing is being produced on the screen. Then the beam moves so it starts to touch the second point source or interface, and it will start to return its echo. Then it will continue to build up that echo across the screen, and there we have the 2 interfaces clearly resolved. Now let's look what happens when we move those 2 interfaces closer together. Beam touching the first one as before. Beam moves across. It hasn't left the first interface. The edge of the beam is still there, but the other edge of the beam has now struck or intersected with the second point source, and it starts to return its echo. So what will happen now is that the beam, as it moves across, never loses sound coming from those 2 interfaces. So the 2 echoes will merge in with each other. Now you might say, oh yes, but look, I can see where it's a little bit darker there in the middle. I can tell there are 2 interfaces. But you can't. How can you be sure that's not just a single complex interface? You can't. So those 2 interfaces here, although separate in the patient, are now clearly not resolved. Okay? So that restricts lateral resolution. Can you see that it depends on how wide that beam is as to whether you could see them separate? Can you imagine in this case here, if that beam was a little bit thinner, it would slip between them and you would see them separate. So lateral resolution is related to and is approximately equal to the width of the beam. Question for you. What will happen if you reduce the beam width? What will it do to lateral resolution? Will it make it better or worse? You say, Brian, for heaven's sake. It's easy. If you reduce the beam width, you improve the lateral resolution. That's why we want narrow beam widths. That's why we focus the beam, to get them as narrow as we can. Here's our focus beam. you will get good resolution within the focal zone. Certainly best at the focal point, but definitely within the focal zone. You will get reduced or poor resolution once you get away from that. So up close to the transducer and further away where the beam is much wider, then lateral resolution is not going to be as good. Now, if you increase the frequency of your transducer, in fact, you will also improve the lateral resolution. Look at our beam width at focus formula. The beam width is 2.4 lambda A on D, where lambda is obviously the wavelength, A is the focal depth of the transducer or the radius of curvature, and D is the active phase of the transducer or the transducer aperture. Now, if we increase the frequency of the beam, what do we do to the wavelength of it? Increase the frequency, shorter wavelength. Shorter wavelength, lower number here, top of the equation line, it'll mean lower beam width, less here. So the beam width actually gets narrower with higher frequencies. So higher frequencies will not only improve your axial resolution, it will also improve your lateral resolution. So lateral resolution is also affected by your output power and gain. Here's a cross-section representation of a beam. If you were looking straight down it and it's coming straight at you. The beam is measured at a specific point at the edge of the beam. The more modern measurement is at the 10 decibel level. In other words, where the highest intensity of the beam, which is in the middle, drops to 1/10 of its maximum value, that is a common place to measure the width of the beam, because it's considered that anything beyond there you're not going to see on your image. Okay, so at this point, there's your beam width. Now, when you amplify the echo more or produce it bigger by increasing the power, it becomes brighter. It also spreads out this bell curve. So yes, the amplitude's bigger, but it also spreads it out sideways as well. And therefore, the beam width will become a little wider here than it is over there. And therefore, increased echo amplitude, you will find that the lateral resolution will degrade. So, same thing as with axial resolution. You don't want to increase that any more than necessary. In a similar way that we've discussed with axial resolution, it's possible your image memory might affect lateral resolution. However, I will say that from definitely personal experience, it's unlikely to affect it, because lateral resolution is always a lot worse than axial resolution. And even with the 256 by 256 image memory, it's unlikely you will ever get lateral resolution down to that level. So the chances are this won't affect it, but potentially it could. And it's worth keeping in mind that image memory may cause a reduction in lateral resolution if you've got a lesser grade pixel resolution. The same with your right zoom feature, exactly the same. You're expanding this over this small area. You're improving your pixel resolution, and it will improve the potential lateral resolution. But my broken record has started again. You can never get better than your beam width geometry. Okay, so that's worth keeping in mind. What will affect lateral resolution on your machine, however, is your line density. The closer you can get your beam paths together, then the better the potential resolution is going to be. And it's adjustable. Most machines will have an adjustment on it to be able to get those beam paths closer together or further apart, depending on what you want to do. Okay, lateral resolution could also be affected by the television monitor resolution. Same with axial resolution. Just a point of note there, you will note that as I've drawn it, that all the little point sources in the patient are shown as very short little lines. In fact, that's the case. Perhaps if you can get an image where the focus is up fairly close and you have a look way down deep in the patient where the lateral resolution is not good, you'll find that those echoes are tiny little short lines, which are approximately equal to the width of the beam. It's an interesting observation. Okay, now let's move on from spatial resolution and let's look at contrast resolution. Contrast resolution isn't related to how small the structures you can see one beside the other. It's related to how well it can differentiate tissues of different echogenicity. Sometimes you can have a very large structure in a patient and it can't be resolved. You can't see it because its echogenicity is so similar to that of the surrounding tissue. I don't know how well this shows up on your monitors, but here we've got a fairly large structure in the image. But if its echogenicity becomes closer to that of the surrounding tissue, it can be very difficult indeed to see that structure. And things like liver lesions, for example, can be very subtle in the differing echogenicity to that of normal liver, and you just might not see them, even though they're quite large. Now, contrast resolution depends on a number of things. One of the things it depends on is the amount of background noise or backscatter interference that you get in the image. Here's a beam coming down through a patient, and it's meeting all these different little reflectors. Now, what's happening there? Each one of those reflectors is scattering sound back up, not only towards the transducer, but throughout the whole patient area there. Now, when they do that, these echoes will start to interact with each other. They will undergo wave interference by adding and subtracting with each other, and they cause very complex interference patterns, which work their way back up or come back up to the transducer, and that causes an overall haze, if you like, on the image. It's an artifact of ultrasound called speckle, and speckle degrades the quality, particularly the contrast resolution of your image. Here's an image or representation of what speckle would look like without any image on the screen. It's just this random pattern of echoes, low-level echoes on the image. Here's an image with little or no apparent speckle shown on it. Now, can you imagine what will happen if we put speckle on top of that? You can see how it degrades, how well you can see all these liver lesions here. In fact, if we have liver lesions that are very subtle within that patient, they would probably disappear with that level of speckle within the image itself. So that speckle has degraded the contrast resolution. The image on the right here has far poorer contrast resolution compared to this middle one. So reduced contrast resolution there. Now, contrast resolution will also depend on your pre and post processing setting that you can set on your machine. For example, dynamic range. The dynamic range, if you reduce it, will mean fewer signal intensities will be used for your 256 or 512 grayscales that you have. What that does is increase the contrast of the image, and that will improve the contrast resolution. I don't know if that will show up all that well on you, but this image has had a widened dynamic range, and this one's slightly narrower. And you'll find that you will see more subtle echoes within the wide dynamic range image than you will in the narrow one. So the contrast resolution will actually improve here, even though you might see lower level, not as many lower level echoes. But it's a way of increasing contrast resolution. One of the other important things that contrast resolution will depend on is your slice thickness. Don't forget your imaging beam is thick in the forward and back plane. Now, in this particular case, we have a beam coming down through, let's call it a cyst. But as you can see, with a wide slice thickness, some of the beam is outside of that cyst, either in front of or the back of, or perhaps even both. Now, when that occurs, the part of the beam that's outside of that cyst is still returning soft tissue echoes. Those echoes are put in the image over top of the cyst itself. Now, this is an interesting case, an example of it that I was involved with a number of years ago. It's a cyst within a breast, and we're scanning with a linear array, and I'm pretty sure you should be able to see that there's a lot of low-level echoes within that lesion. It's no longer a simple cyst, it's a suspicious lesion. So what we did was we picked up the transducer, took it off, the linear array, and put on what was called an annular array. It's an old type of sector transducer. But when we did that, look what happened. All those echoes completely disappeared. That lesion became a simple cyst. It got rid of these artifactual, as they turned out to be, artifactual echoes. Why did it do so? Because an annular array transducer focused very well in both planes, not only in your beam width plane, but also in your slice thickness plane. It did this. So when the annular array scanned across here, as the beams went through this cyst, the beams were totally within the cyst, not in any soft tissue in front of or behind. And therefore, it did not return any echoes. If the echoes were still there, they would be echoes coming from within this lesion, and they'd be real. It showed these echoes up here to be artifactual, caused by slice thickness. So slice thickness is very important. Thin slices improve contrast resolution. Now, contrast resolution will also depend on the machine itself, the inherent characteristics. So some machines are better than others. You improve it by using appropriate gain and power settings, including a TGC. So don't have your gain and power turned up more than necessary. Drop your dynamic range. Use of harmonics, which is something that you will learn about. When you use harmonics button, what harmonics will do, one of the things it does is reduce the amount of speckle that you get. Remove the speckle, you improve the contrast resolution significantly. Use matrix transducers if you've got them available. Matrix transducers actually focus, variable focus the image in the slice thickness plane as well as the beam width plane. They're superb. Most transducers use a lens in the slice thickness plane, which is set as weak focusing, and you wind up with a moderately thick slice thickness. But a matrix transducer doesn't. This is just a reminder to you about a matrix transducer. Conventional transducers will have a lens across the slice thickness plane with the transducer elements going across like that. And the lens will focus in that plane, and it will be moderately thick, especially when you get away from the set, fixed focal depth. But a matrix transducer has multiple elements across the face, and as you focus the beam down axially, it will also focus the beam across in the slice thickness plane. Brilliant. But they're expensive. Your machine may not have matrix transducers available. If it does, it will improve contrast resolution. Okay, now the third resolution I wanted to talk about is temporal resolution. Temporal resolution is time resolution, the ability to be able to look at moderately moving or rapidly moving structures. Now, to do this in B-mode ultrasound, you need high frame rates, particularly with cardiac sonographers. You're looking at heart valves, obstetric sonographers, you're going to look at little fetal hearts and that. You need high frame rates. Okay, now the frame rate basically depends on how many beam paths you have in the image, number of scan lines, and how long it takes to acquire each scan line. So there are many times during your scanning, you will be trying to improve your frame rate to get better temporal resolution. Okay, so these are the different ways that you can do it. First, and foremost, decrease your scanning depth to the minimum necessary. If you do that, the machine does not have to wait as long to get the echoes coming back to the transducer before it can send out the next pulse. So the frame rate increases. Decrease the number of scan lines you're using. Now you can do this in a couple of different ways. One is to reduce your field of view, your lateral field of view. Some linear array transducers will allow that, some won't, but most of your sector or curved array transducers will. If you reduce your field of view, what the machine will most likely do is drop off the beam paths that are needed out in the full field of view, and that reduces the number of scan lines, and that will improve your frame rate. Alternatively, you could drop some of the scan lines out by decreasing the line density, and most machines have this control available to you. It may be called line density control or resolution control, and you could have a couple of different settings. If you are able to do that, you will drop the beam paths out, reduce the line density, improve your frame rate. The trade-off is your lateral resolution will be degraded a bit, but temporal resolution might be more important. Your decision, you're doing the scan, but you have a choice. If you are using multiple focal zones, drop down to a single focal zone. Okay, so don't use multiple focal zones if you want high temporal resolution. But on the other hand, that's fairly logical. Use your right zoom feature, because when you do that, you're effectively changing your scanning depth and your field of view width. So that will improve your frame rate. Turn off compound imaging. I'm not describing compound imaging to you, but it's a feature that a lot of machines have. If it's switched on and you're using multiple frames to produce a single image on your screen, turn it off, so you're only using the single frame. If you have frame averaging, sometimes called persistence, turned on, turn it off. It won't affect the frame rate, but it will affect your temporal resolution, because it's using multiple frames to produce your image. The idea is to try to reduce some speckle. So turn that off. All those things will improve your frame rate. Just one thing, if you do happen to have a machine with multiple beamformers, you will find that your frame rate is much better. So if you've got a really good machine with quite a few beamformers in it, probably going to be a fairly expensive machine, you will find that you may still be able to use multiple focal zones and still have a very high frame rate. That would be brilliant. But you can't switch this on and off, okay? You either have multiple beamformers or you don't have. So I'm sorry, it depends on the machine. Okay, now just one other little comment to make here. Temporal resolution, good question. Is it better in N mode, Doppler, or B mode? Or is there any difference? Well, in actual fact, N mode, and I'm talking about spectral Doppler, not color Doppler, both of those use a single beam path to produce the data set coming back up to the machine, whereas B mode is using multiple beam paths. N mode and Doppler are doing it at the pulse repetition frequency. Okay, so that could be 500 to 1,000 times per second, whereas B mode is much slower. Watch. Here's a B mode image being gradually being built up, while N mode and Doppler are getting that data back all the time. Watch that again. Watch the B mode. Oh, look at it, it's taking forever to build up a single frame, while N mode is getting that dynamic information back very rapidly, up to more than 1,000 times per second. This one might be set at about 50 or 40 frames per second. So you can imagine that the temporal resolution is much better in these two. Yes, it's not showing you anatomy, it's not showing you a lot of different parts of the patient, but the actual dynamic aspect of it is much better. N mode would probably be better because it's at the maximum PRF. Doppler, you adjust the PRF or your velocity scale to suit your individual circumstance. So you may well have slowed down your PRF in Doppler to suit. So If I was a choice of putting him in line, N mode's best, followed by spectral Doppler, followed by B mode. So that's it on resolution. That's all I want to talk about. So over to you for questions, and hopefully you've got a few interesting ones for me to try to answer. Thank you.
Wonderful. Thanks so much, Brian, for another great presentation. You covered a lot in there. So we probably have about 10 minutes or so left of time. So we'll just go into a bit of Q&A if you are ready for us.
No problem.
Fantastic. Great. So let's go into the first one. I'll just change my slide here. All right. So we've got a question here. What actual axial and lateral resolution could I expect from my machine?
Well, obviously it's going to depend on quite a few things. As I said in the session there, it's going to depend a lot on the frequency of the probe. So I'll give you an example, perhaps. Let's suppose you had a 3.5 megahertz transducer. And we need to start to set a few parameters. For example, we need to set the aperture of the transducer because that makes a difference to the beam width, and that'll be lateral resolution. And we would need to know how many cycles there are in the pulse, which will affect axial resolution. So let's assume 3.5 megahertz, 2 centimeter diameter aperture, 4 cycles in the pulse. Pretty average. Maybe the new machines are getting down to 3 or 2 cycles now, but let's start at that point. If the focus is set at, say, 8 centimeters down in the patient, then the axial resolution you can expect from that machine, that transducer, is about 0.88 of a millimeter, which is pretty impressive. The lateral resolution, however, would be 4.2 millimeters at the focal point, and that's not very good. Now, obviously, if we went up to a 7 megahertz transducer, that would halve because it's a linear relationship. So a 7 megahertz transducer, you could get down to 0.44 of a millimeter of axial resolution and 2.1 millimeter at the focal point. And then, of course, if you shorten the pulse with fewer cycles, you can change it. But that might give you a bit of an idea. The important thing from that example is to see the difference between axial and lateral resolution. We had axial resolution, for example, at 0.44 of a millimeter. The lateral resolution was over 2 millimeters. That is why if you're trying to measure something extremely close together, very close, for example, the thickness of a gallbladder wall, or a nuchal translucency in an obstetric scan, which might only be a couple of millimeters. Always use your axial resolution to do this, not your lateral. So always have those two interfaces, one on top of the other, vertically, so that you can use the beam, the axial beam coming down to measure them. Do not put them so that the interfaces are side by side, because the lateral resolution to see those two apart is very poor. So always use axial resolution for small distances. If you're looking at something large, the distances are a fair distance apart, not so important, because a very small error there is not going to make a significant difference to your overall diagnosis. So that's fine, but close together, axial resolution. Sorry, that was a long answer, but I hope that's answered your question.
That sounded pretty thorough to me. Thank you, Brian. On to our next question. You said that the use of harmonics improves contrast resolution. Does harmonics have any effect on spatial and temporal resolution?
Yes, it can. It depends on the sort of harmonics that you have in the machine. This is not a harmonic session, but there are two basically different sorts of harmonics you can use. A very simple one with a single pulse going down, or you can use the later versions of pulse inversion type harmonics where they use two pulses. Now, if you're using a single, a less expensive, simpler harmonics using a single pulse, what they found with harmonics is the very broad bandwidth of our single pulses was a problem. They couldn't separate the first and second harmonic frequencies well. So what they have to do with the simple harmonics is actually extend the spatial pulse length or the pulse duration, which is effectively the same thing. By doing that, expanding it, they narrow the bandwidth, the frequency bandwidth of the pulse, and harmonics will operate better and you can get good harmonics. But if you've got simple harmonics and you switch it on, then probably they've extended the length of the pulse a bit, and that will reduce your axial resolution. Okay. Now, if you're using the pulse inversion type harmonics, using two pulses, because you're using two pulses along each beam path, it takes longer to do it, twice as long. And therefore, you will keep your nice axial resolution, but you will degrade your temporal resolution. So it does depend on what you're doing. If you're not sure of what harmonics you have, just look at the frame rate before you switch it on. Hit the harmonics, the tissue harmonic imaging on, and look at the frame rate and see if it falls. If it drops, you are using the later version pulse inversion type harmonics, and your temporal resolution will be great. If it doesn't change, then the chances are your axial resolution has degraded a little bit. Hope that's answered that one for you.
Sounds like some very handy tips there, Brian. Thank you. And just a reminder that thankfully everyone will get a link to the recording of the webinar. So if you guys do need to rewatch some of this back, that will be accessible to you guys, as well as Brian has kindly provided us some handouts, which are attached in this evening's webinar. Brian, I think we've just got time for one last question. And that is there any way to compare the contrast resolution of two different transducers or machines?
Not easily. Yes, you can do it. What you would have to do is use a tissue equivalent phantom, if you can get hold of one. And if a lot of general phantoms, quality control phantoms, will have small simulated lesions in them of different echogenicities and different sizes. And with these, you could scan this particular phantom with one transducer, have a look at the images, record them, and with similar settings, put another transducer on and see if you can see those lesions better or more lesions using the other transducer. So that would qualify or virtually quantify how well that contrast resolution is on the machine. You could do that with two different machines using the, say, 510 curved array transducer on one machine, look at the phantom, and then scan that same phantom with a similar transducer on the other machine and see what the difference is. But you would need to get hold of one of these phantoms. And an even better phantom is a dedicated contrast resolution phantom. But they're going to be pretty rare unless you're in a research area. But you might have a research hospital or department near you which may have one of these phantoms available, and you might be able to borrow them. Or you could ask the manufacturers, do they have a phantom in their department or their office? And could you borrow it for a short time to have a look at your machine? Hopefully they would allow you to do that. Just one other thing with contrast resolution. A lot of machines are coming out with some very clever mechanisms or processes within them to try to reduce that speckle I was talking about. And if you can reduce speckle, you improve contrast resolution. Things like Philips have got something called XRES, which is a fairly complicated mathematical process they run on the image, and that cleans up the image. And other machines would have something similar. Anyway, sorry, I'm getting a bit off track.
No, thank you so much, Brian. Your wealth of wisdom is always so appreciated. So thank you so much for giving up your time over the past few weeks and so close to Christmas for joining us online tonight. We really do appreciate it.
No problem.
And thank you to the rest